Okay, so when in the original description of the conference, I think that Kelvin described, at least to me, that the theme was going to be the first person in physics. And that made me reflect on why in quantum mechanics, the first person suddenly becomes important. Because the first person was always there in physics, because physics is about the world and persons are part of the world. But I think we developed ways of dealing with it in classical physics that worked well for a long time. So when we're dealing with open subsystems, so particles, complex systems, we keep ourselves out of the systems that we're studying. So we treat ourselves as exogenous and our interaction with the system as intervention. So we're not part of the subject matter. But the features of the universe and when we're dealing with the universe as a whole, we are implicitly part of the subject matter, but the features of the universe that we're usually interested in are large scale and far away, so they're unaffected by our own activity. And imaginatively in those contexts, we tend to take ourselves out of the universe when we're thinking, picturing it as though it were an object that we're looking at from the outside. All of this is a convenient and mostly harmless fiction in classical settings, but it pushes out of view a phenomenon that I'm going to call interference. So not to be confused with quantum interference. And I'm sorry, I couldn't think of a name that was as apt and that didn't risk the confusion. But when I say interference, I'm going to be talking about a phenomenon that I'm going to introduce below. So think of it as capital I interference. Okay. So interference is present in both classical and quantum settings. But what I'm going to suggest is that seeing how the phenomenon that I'm going to be talking about plays out in classical and quantum settings gives us a new way of understanding the differences between them. So I'm going to introduce, hang on a sec. I'm going to introduce, my slides aren't advancing. I'm going to introduce interference and give some examples distinguishing it from disturbance and ignorance. And the suggestion is going to be that interference is unavoidable in any setting in which a system is representing the domain in which it's situated. And that's going to make it impossible to stabilize certain features of the world as objects of knowledge. How interference propagates depends on the way that the domain is connected. So in a classical setting, interference is channeled and focused into the future. But in a quantum setting, interference is endemic. And I'll argue that this is one clear way of understanding the sense in which the universe is participatory and explore different ways of understanding that in a realist mode. So most day-to-day physics, as I said, one is modeling other systems, so cells, gases, and we maintain a provisional separation of subject and object, or investigator and system being investigated. Ultimately, though, we are part of the universe. We act in the domain that we're representing, and that can create problems that make it difficult to stabilize certain facts or certain features of the universe as objects of knowledge, things that we can even potentially know. Okay? The people that have encountered this unavoidably are people that are trying to program an artificial and general intelligence, so an AGI. They want to program a system with a bunch of general knowledge and the ability to model the world. And they're sort of coming up against the fact that some of what happens is stuff that the computer does. And that creates a kind of interference. So let me give you a simple example. Suppose you want to program a computer that's going to serve as our grand overarching database for the universe. So repository of information about everything. We begin programming it with as much factual information as we can about the world. So we feed it the laws of physics and all of the scientific knowledge that we've amassed. We add facts of history. We add facts about the monkeys of Costa Rica and the vast reaches of space. And the goal is to be able to put any question of physical fact to it. And the answer is going to appear in an output channel. Okay, so there's an input channel, an output channel. It's not hard to find a question that it can't truthfully answer. Okay? So you just ask it, Is the answer to the question that's about to be displayed on the output channel? No. So you think this through, any answer it gives will be false. It answers yes, clearly it's wrong, since that misdescribes what it wrote. And it answers no, it's wrong as well. Okay, familiar sort of anomaly. It might seem like just an anomaly, a special case. These kinds of problems are familiar, of course, to philosophers, certainly to computer scientists. The problem is that what the computer does in giving the answer interacts with what it says negatively by rendering what it says false. Okay. So the first answer, the first reaction one might have is to try to suppress the difficulty. So maybe you try to keep these kinds of questions from arising. More subtle to accomplish than you might think, since there's nothing wrong with the question that's being asked. It's a question about a perfectly mundane matter of physical fact, one that any other computer could answer truthfully, and indeed that it could itself answer truthfully at any other time. Another thought is to acknowledge the difficulty and try to quarantine it. Again, this is more difficult than you might think. That question, that fact, is a node in a highly connected network, and there's no general way of isolating its effects. So if the word no appearing on my screen at t is going to affect the truth values of other propositions, for example, other computers in the room are going to record my answer, a person who walks into the room is going to see it, someone might take a picture, the electricity on the screen, the lint in the air, all of these things are going to be affected by what appears on my screen at a particular time. They will affect other things. The effects are going to ripple through the network of truths. So from the point of view of knowledge, one wants to get as close to minimizing any disturbances that the computer's own activity has on the truth values of sentences in the field that it's representing. So we're imagining a field of propositions it's representing that are sort of representing facts in the domain. The reason that the problem, the reason my things aren't advancing, the reason that the problem arises is that by saying things, the computer is doing things. And that's creating interference between what it says and what it does. Logical paradox is a form of negative interference. What the computer says conflicts semantically with what it does by rendering it false. Nothing mysterious here. What's happening is that the computer can't stabilize the fact that it's meant to describe, namely the word that appears on the screen, independently of giving the answer. And the thing is set up so that no matter what answer it gives, what it does in giving the answer conflicts with what it says. Negative interference can arise in less direct ways than that. So I started with it because it's the clearest case. But imagine this, a boy tries to guess a Christmas present every day from June to December. He comes downstairs with a new guess. He's been thinking all night. Unbeknownst to him, his mother's just waiting until Christmas Eve to make the purchase, and she's determined to surprise him. Okay. Negative interference. Poll predictions prompt responses that counter the predicted events. So predictions of Republican victory prompt Democratic turnout. Predictions prompt people to change their votes to make strategic choices given where other votes are falling that reconfigure the whole field. Interference is different from ignorance, and it's different from disturbance. Okay? So in the case of ignorance, there's a fact that's well defined independently of our knowledge. We simply don't know it. In the case of disturbance, there's a fact to be known. So for example, imagine that you want to know if your kids are asleep, so you turn on the light to check. In a case like that, there's a perfectly definite fact that you're trying to find out, namely whether your kids were asleep. It's there independently of whether you look, but the attempt to measure it fails because in the course of trying to measure it or ascertain it, you change the state. And so you break the correlation between what you see and the fact that you were trying to determine. In the case of interference, the fact to be known is connected to our knowledge of it in a way that makes it impossible to stabilize independently. In that case, so think again about the computer trying to answer the question, there isn't a fact there to be known. There isn't a fact, as I'm going to put it, there anyways, or there already, independent of our knowledge of it. So you understand, think about the boy with the Christmas present. In that case, you understand what's going on. The fact to be known is connected to his questioning in a way that makes it impossible for him to stabilize independently. In this kind of situation, where the fact being represented is connected to the representation of it, the epistemic attitude doesn't really work. The logic of knowledge sort of presupposes that the object of knowledge is there to be known, or again, as I'm going to put it, there already, or there anyways. As long as one's own activity is connected in the domain that one is representing, some of what one encounters will be ripples produced by one's own activity. And one can't treat, I'm going to suggest, those features of the landscape as potential objects of knowledge. So it wasn't hard to find examples of interference in a classical setting. I gave you a number of them. And it's genuinely problematic. The sort of interference I'm talking about is genuinely problematic in some domains. So the boy and his Christmas present, that was artificially arranged, right? But stock predictions and election polls, any case where predictions become public and affect the course of events being predicted, in those cases, you really can't stabilize what you're representing independently of the act of representing it. Knowledge is possible in a classical setting because this sort of interference is controlled and it's disciplined. So everyday perceptual interactions are unaffected by this kind of interference. These exchanges, perceptual interactions, have the logic of measurement. I interact with an object. My state after the interaction is correlated with the state of the object before the interaction. And this allows us to stabilize the spatial environment as an object of knowledge, something that I can undertake inquiry about. And that will, in its turn, stabilize the past, since the spatial environment contains systems whose present states contain information about the past. So fossils, footprints, written chronicles. You can think of these things as measurements of the past. The states of these objects is correlated with the states of objects or events in the past. So in a classical setting, the external environment and the past are, from our perspective, sort of there to be known. They're things that we can take an epistemic attitude towards. The thing about the future, things are different in a classical setting when you think about the future. So philosophers tend to picture knowledge as a relationship between a kind of transcendent subject and eternal truth, but it's not. Knowledge is embodied and it's efficacious. Knowledge makes a difference in the world. It's the whole point of knowledge from an evolutionary perspective is to guide action. Present knowledge guides action, making it impossible for an embodied agent to stabilize her own future as an object of knowledge for exactly the reasons that we've been talking about. Anything you predict, you can act to forestall, avoid, deter. This is just the internal version of the pollsters and the election outcome, predictions feeding back into the domain and affecting the outcome. In a way, agency is the enemy of knowledge. We saw above that when we were talking about the computer, which would be the sort of grand depository of all truth, from the point of view of knowledge, from the point of view of making it the embodiment of knowledge, we wanted to minimize the disturbances that the computer's own activity had on the domain that it was representing. Remember, that was one of the suggestions about how we might suppress the difficulties created by interference. But from the point of view of agency, we want to use knowledge to guide action. We want to make knowledge as active and efficacious as possible. Present knowledge guides behavior, acting on its own predictions in a way that makes it impossible to stabilize the future, her future, at least for an embodied agent, as something that's sort of there to be known, something that it's appropriate to take the epistemic attitude towards. Trying to stabilize the future as an object of knowledge is like chasing your own shadow, or like the child trying to guess his Christmas present. In that way, and for that reason, I want to suggest, for an embedded agent, for us, the future isn't there to be known. So the kind of instability that I'm talking about isn't mysterious. It's not mysterious it's not paradoxical, it's not mysterious in a kind of philosophical sense. It doesn't threaten, for example, objectivity or realism. It doesn't even really have to do with truth. The objective facts are the objective facts. What's true is what's true. It's just that our own knowledge and our knowledge gathering activity is connected in the world. Present knowledge interferes with future fact and makes it impossible to treat the future as something that is, again, there to be known, there independently of how we represent it, there already or there anyways. This is a feature, not a bug. It's what makes agency possible. That's what agency is. It's using present knowledge to affect future fact. The agent anticipating the effects of her own actions and using her knowledge to avoid or forestall things she doesn't want and to promote or encourage ones she does, is effectively exploiting the interference effects of her own knowledge. Now, this isn't simply an epistemic fact. Our world is constituted in part by knowing agents, acting in ways that depend on their knowledge. So that means that our universe as a whole isn't there to be known independently of our actions, simply because it includes us, and our actions are part of what happens. What we can and cannot stabilize as potential objects of knowledge depends on the way that our own actions are connected in the world. In a classical world, we can take an epistemic attitude to the spatial environment and to the past. But any attempt to stabilize belief about the future, I'm suggesting, is going to encounter interference. So far, so good. What about quantum mechanics? What we see in a quantum world is that interference is endemic. So those intensively analyzed interactions, sorry, let me back up a bit. The theory itself tells us that quantum measurements, what it calls measurements, that is, attempts to find things out about the quantum world, those interactions that bridge effectively the effectively classical world of observers and quantum systems, those interactions don't have the logic of measurement in the specific sense that we cannot stabilize the properties of quantum systems independently of our attempts to know them. So for example, of course, in double slit experiment, whether we see wave-like or particle-like behavior depends on whether we place particle detectors at the slits to observe position. And more generally, any interaction between a situated agent and a quantum system that we might try to use to get information about the system. So anything that we would call a measurement in quantum mechanics, the statistics of which are predicted by the Born rule, interferes with the properties of the system in the specific sense that I was talking about. The difficulty has always been in quantum mechanics, trying to understand what things could be like in a quantum world in such a way that we could explain the empirical predictions of quantum mechanics. And the logic that we bring to our attempts to understand these are the ones that are appropriate if there is no interference. So for example, we assume that unmeasured quantities have values, We assume that if we perform a measurement and obtain a result, that result reveals what was there before. We assume that if we predict with certainty the result of if we can predict with certainty that the result of a measurement would be X, we could infer that the quantity has the value independently of the measurement. We assume, that is to say, that the property that we observe is one that was there already or there anyways. And then we find that the logic of quantum mechanics doesn't support those inferences. It doesn't allow us to treat the results of quantum measurements as revealing something that was there already or there anyways. The lesson of the last century in research in quantum foundations, so the history of no-go results from Gleason through Cauchy-Specker to BBR to Froschinger-Renner to Bruckner, all of these establish in various ways that Schrödinger evolution does not allow us to produce Born statistics if we hang on to the idea that these interactions are revealing antecedently existing categorical properties of measured systems. And there's, of course, a history of increasingly careful analysis to locate the source of the problem, history of interpretations that either modify dynamics or relax aspects of the there already or there anywayness to try to accommodate them. But this isn't an entirely alien phenomenon. We cannot stabilize properties of quantum systems as objects of knowledge. I'm suggesting in the same way and for the same reason that the child can't stabilize the Christmas present as an object of knowledge. There simply isn't something there to be known for us, independently of what we might try to find out about it, independently of the questions we put to nature in the form of measurement interactions. Quantum mechanics reveals that the stability of the world is only apparent, that the structures that are needed to stabilize the world is something that's there to be known. Indeed, the structures that are needed to stabilize ourselves as knowers, and the structures that are needed to stabilize a conception of ourselves as I's and agents in the world, and the world as an it, are present only in an effective and emergent way. But that doesn't mean that there is no world, only that the world isn't there to be known for us in a manner analogous to that in which the future isn't there for us to be known for us in a classical world. In many ways, I think, sorry, I can get this to change. In many ways, I think this is just repeating things that we already know about quantum mechanics. So why is it interesting and helpful? I think it gives us a way of seeing the difference between the classical and quantum world that demystifies some of the weirdness of quantum mechanics. The phenomenon of interference is incontestable. It's just an artifact of the logic of representing something that includes you. Any system that acts in the domain it's representing is going to encounter interference. It arises in a classical setting as well as a quantum one. And I started with those simple examples because I think it's easy to understand what's going on in the classical setting with mundane examples like the boy and his Christmas present. The difference between the quantum and classical worlds is not that there's interference in one case and not in the other, but in how pervasive interference is. And it focuses on interference and foregrounds the fact that the conditions that allow knowledge in the traditional sense, that is the stabilization of the world as a potential object of knowledge, the separation of knower, the knower's activity, and the world as an object of knowledge, those conditions are special, they're not generic. So I entitled my talk, A Participatory World Universe in the Realist Mode, because I see what I'm saying is actually aligned with Wheeler's idea of observer participancy. So this is Wheeler's drawing from a sort of famous article. Wheeler introduces the idea of observer participancy to describe what he called elementary quantum phenomena. And his basic insight is that observer participancy, where he hyphenates it as a single word, is the basic phenomenon. It's the general case, the ability to separate observation from participation, and to stabilize the world as something that can be seen and known, and with it, observers in the sense of emergent structures that interact with their environment in ways that obey the logic of observation, where its state is uncorrelated with the object in advance that it's representing. That's the special case. So we see this sort of diagram, the one on the left here, everywhere, where we separate the agent from the environment, and we think of it as coupled to the environment by these two pathways. There's perceptual pathway going in this direction, the action pathway going in the other direction. But of course, the actual situation demands that we put the agent in the world. The agent is acting, the agent is acting in the environment that it's representing. And some of what it sees will be the ripples of its own movements. The environment that it's representing will unavoidably create interference and will sort of constrain what it can stabilize as a potential object of knowledge. Because its own knowledge guides how it acts, what the agent can stabilize as an object of knowledge and hence take a purely epistemic attitude towards will depend crucially on how its own actions are connected in the world. The difference between the classical and quantum world is not that one is participatory and the other is not. It's that in the classical world, the interference caused by the observer's own actions is focused and channeled into the future. The spatial environment and the past are uninfected with interference. What you know isn't going to make a difference. In the quantum world, by contrast, it is pervasive. So what should one's attitude be in cases where interference is present? It should be the attitude of the participant, not the attitude of the observer. We know both of those attitudes, the attitude of the participant and the attitude of the observer, because we live the position of the participant in our daily lives. The logic of these interactions, of the participatory interactions, is not the logic of measurement, it's the logic of choice. So think about what a choice is. A choice produces an action that interferes, a choice represents, an action that interferes with what happens. I make my choices strategically, exploiting that interference. So for example, I want a crop in the fall, I plant seeds in the spring. I want protection when the rain comes, I fix my roof. I want pasta, I want my pasta overcooked, which I always do. I leave it in too long. Okay? The mistake that the boy makes, the boy with his Christmas present, in questioning his mother about the Christmas present, is that he treats the interaction as a game of knowledge. And in that capacity, his failure is guaranteed. If he treats it as a game of strategy, he can use it to get what he wants. Our attitude towards the quantum world, I'm suggesting, should be something like our attitude to the future in a classical setting. Quantum measurement should be reconceived as the results of quantum choices. So if you think about the logic of measurement, measurements are characterized implicitly by the absence of interference. There's a suite of counterfactuals that are supposed to capture the idea that the results of a measurement interaction reveals facts or properties that are there anyways or there already. We assume that the values observed obtain even if no measurement is performed, and even if a different measurement is performed. We assume that unmeasured quantities have values. We obtain a result. That result would have obtained even if we didn't perform the measurement, just to make the counterfactual explicit. And if we could measure A and could measure B, then the values we get for A and B are compatible, and on, right? So there's a suite of counterfactuals that surrounds the logic of measurement. What about the logic of choice? Why is this not working? There we go. we don't expect any of the things that are connected to our choices to be there anyway, or to be there already. We expect what happens to be tied to what we choose so that it doesn't happen whether or not we make the choice. We don't expect the results of one choice to be compatible with those of another. None of that suite of problematic counterfactuals holds in the case of choice. Ordinarily, of course, we would understand all of this in causal terms and against the background of a certain conception of time. So we imagine that we live in a universe that's unfolding in time, that causal relations run from past to future. And that's why we regard the past as fixed and the future as open. That's why we take an epistemic attitude, that is to say, towards the past, and a strategic attitude towards the future. And then we bring those ideas about time and causation into a quantum setting, and it doesn't work. We don't know how to impose those ideas on the phenomena that we're seeing. But we want to keep those ideas, those everyday ideas about causation and time, out of here. Our everyday ideas about causation and time, how many of you recognize the finger wag here? So our ideas about causation and time grew up in a classical setting where they are natural expressions of facts about how interference propagates in the classical world. If we look at the physics itself, the facts about how interference propagates are explained by deeper physics that makes no mention of causation and that rejects that understanding of time. So the explanatory direction goes from facts about the way interference propagates in a classical setting to the ideas about time and causation that build those into a kind of metaphysical picture that frames our everyday thinking. But the actual metaphysics of a classical world, at least since Einstein, doesn't support that. So the actual metaphysics of classical physics since Einstein doesn't support that picture. Relativistic universe is a four-dimensional manifold of events with no global conception of time. So there's no unfolding, and the laws don't incorporate any intrinsic direction of determination. So suspend those everyday ideas of time and causation, so push them into the background and just try to understand things simply in terms of how interference propagates. It's convenient to sort of get yourself into that way of thinking, just to imagine virtual worlds where you get to set the rules and you get to say how things are connected. And then you get to sort of introduce an agent whose actions activate different nodes in the network. How the activation propagates is determined by how the network is connected. And that in its turn will determine what the agent can treat as an object, as something that's sort of there to be known, and what it can regard, what it has to regard rather strategically in making its choices about what to activate and what not to activate. So Wheeler was also someone that made the suggestion that quantum measurements should be reconceived. Sorry, I can't get to say, sorry, hang on. That quantum measurements should be reconceived as choices. And he emphasized the participatory character of our interactions with the quantum world. So do you remember Wheeler's analogy of the game of 20 questions that he used to sort of illustrate the difference between classical and quantum world? Chris tells me that this actually happened to him they played this trick on him at a party once. So in the ordinary version, one person, the contestant, is left outside of the room while the others, the players, agree on some object. The contestant is then allowed back in and puts questions to players that they have to answer truthfully. The contestant wins if he guesses the object that they had in mind within 20 questions. So in Wheeler's version of the game, the players, unbeknownst to the contestant, don't agree on an object in advance. Whoever's asked the question by the contestant, so they let him out of the room, they don't tell him anything, but they let him back in and he starts asking questions. Whoever gets asked the question by the contestants gets to answer in any way he wants, so long as his answer is compatible with all of the answers that went before. And then the last player gets to decide whether the game is won or lost. So the difference between the two games is that in the first game, the questions have an epistemic character. There is an object that's there anyway, that was agreed in advance, right? There's some antecedently agreed object. In the second game, the object is being sort of sculpted jointly by the questions and by the responses of the players, and it's being done in real time. So here's what Wheeler says about it. The world we once believed exists out there independently of any act of observation, just as I, entering, thought the room contained a definite word. In actuality, the word was developed step by step through the questions I raised, as the information about the electron was brought into being by the experiment that the experimenter chooses to make. That is, had I asked different questions or the same questions in a different order, I would have ended up with a different word, as the experimenter would have ended up with a different story for the doings of the electron. So it is, of course, very difficult to really figure out what Wheeler actually thinks about quantum mechanics. From the perspective of quantum foundations, most of the people that take an inspiration from him have gone in the direction of cubism. So they've seen their view as a radical departure from classical, kind of classical conceptions of physics. Their view is defined in opposition to realist views that treat the wave function as describing an objective world. So according to cubists, the wave function is the user's manual for an agent, a tool that can be used to guide expectation of future experience on the basis of the past. That's certainly one direction that one can go, but I don't think that the features of quantum mechanics that I've been pointing to need to push in that direction. Again, I don't think it needs to be thought of as about realism. It's about knowledge. It tells us that the quantum world isn't there already or there anyways for embedded observers, not because there's no world or no objective world, but because there's no observation in the classical sense. Every interaction is participatory. Even in a classical world, of course, as I said, we are participants, and we can't treat the world as a whole as there already or there anyway, simply because it includes us. We're going to run up against the sort of self-reference problems that the computer did. In that most basic sense, some of what happens doesn't happen unless we do it. That basic self-referential kind of interference affects other parts of the landscape as well in a classical world. But because of the way that interference is channeled in a classical world, there are large parts of the world that we can stabilize independently of our own activity and our own attempts to know it and treat as objects of knowledge. So as I said, perceptual interactions with the spatial environment, those have the logic of measurement. Because the spatial environment contains information about the past, and again, I mean, there are physics questions about why that's so, that have answers. But both of those, the spatial environment and the past, in a classical setting, we can treat as the fixed background against which our actions occur, and interference runs into the future. But quantum mechanics tells us that our world, insofar as it is quantum, is more pervasively participatory than we thought. It tells us that our interactions with the quantum world have the character of the boy's attempt to guess his Christmas present. It tells us that we should approach our interactions with the quantum world, I'm suggesting, in the way the boy, if he understood what was going on, should approach guessing about his Christmas present, or in the way that a savvy player in Wheeler's version of 20 questions should approach his play, namely strategically, not with a purely epistemic attitude. To see, though, that all of this can be accommodated in an objective ontology consider how it goes in an Everettian setting. Just because it's the simplest and most straightforward and most kind of uncompromisingly objective ontology, one that uncompromisingly accepts the quantum dynamics. And because the wave function is reified in the Everettian setting, it gives us some indication of how it might be treated on other objective ontologies. So let me back up a bit. So there's a discussion in the sort of Evans-Strawson tradition in analytic philosophy that has its root in Kant, that talks about how the mind stabilizes a conception of self and world out of the flux of experience. This account is a conceptual one, so it talks about constancies in experience and how the self becomes stabilized as a subject or knower at the same time that the world becomes stabilized as an object. Experience is conceived as a relation between subject and object and interpreted as a view of a world from the perspective of a body moving through it. So it's a kind of, mental computation that performs this stabilization by separating, changes in experience due to my movement and changes in the world, changes in experience due to changes in the world. So Marr's simple theory of perception is sometimes used as a template, where the idea is that you start with visual experience and the mind factorizes changes in experience into changes in the world and changes in one's own position in it. The computation is one that minimizes change along both dimensions, kind of imposing an order on what would otherwise be just, a kind of array of changing sensory experience. So this is an epistemological or broadly cognitive psychological story, a story about how experience becomes articulated. The raw material for that story is experience, and the world gets discerned in experience. In the context of any physical theory, that story has to be paired with an ontological story that starts with whatever the theory treats as basic and shows how subjects arise and experience gets recovered in a world of the kind that it describes. So in Everettian quantum mechanics, the wave function is a basic object. T-coherence provides a physical mechanism for the suppression of quantum interference that tells us how the sort of branching structure of internally classical looking worlds arises. It's in the context of these classical worlds, the histories of which form the branching structure, that observers arise and that the world becomes stabilized as a potential object of knowledge, that is, as something that's there to be known independently of our attempts to know it. So the account of how the classical world emerges from the quantum one is effectively an account of how a space is opened up for information consuming agents that accumulate knowledge and use it to guide action, guide behavior. Quantum mechanics itself tells us how those conditions arise by telling us how the classical regime, and hence the sight of knowers in an objective world, is stabilized out of the quantum one. It also tells us why attempts by classically situated observers to stabilize quantum systems as objects of knowledge fail. They fail because the quantum dynamics itself tells us that quantum measurements are not measurements. They don't have the logic of measurement because they lack that sort of already there-ness or there anyway-ness. That whole suite of counterfactuals is not supported by the quantum formalism. But these two pieces fit together nicely. You get in an Everettian setting, you get an understanding of how a conception of self and world is stabilized out of experience, and an understanding of how a classical world that supports the emergence of information consuming systems arises from a fundamental ontology. And in addition, there's a sort of worry that's plagued participatory accounts of quantum mechanics about the role of the observers. So people often think, look, if observers bring the properties of electrons into being, what brings them into being? Right? I think there's less of a worry here in an Everettian setting because observers emerge as inhabitants of the universe as decoherent stabilizes classical world histories. That is, observers themselves arise only as emergent structures. So I said that I'm almost done. I said that quantum measurements should be reconceived as quantum choices. It's not an accident that I think that accounts of quantum mechanics that treat measurement in a quantum way, so account interpretations that bring measurement under the quantum dynamics, treat it implicitly as having the logic of choice. So I think it does in the setting of, in an Everettian setting. In an Everettian setting, what we are choosing when we choose to make a measurement. So choose whether to check the cat in a delayed choice experiment, choose whether to place detectors at the slits. What we're choosing is to decohere the wave function. And what measurement we choose will be a choice about which sorts of branches to decohere it into. In relational quantum mechanics, for example, another version that really does respect the quantum dynamics, we're choosing to couple with, when we choose whether to make an observation, we're choosing whether to couple with other systems, and these couplings produce relational facts. So cat live or dead to me, particle through left slot or right slot in relation to me. If you look at quantum mechanics through these lenses, what I have said, I think, makes us aware that the conditions that need to be in place for articulation of subject and object and stabilization of the world as something that's a potential object of knowledge, those conditions are not generic and are only satisfied in an effective and emergent way. So you see the dissolution of those structures at deeper levels. Quantum mechanics reveals a substructure to everyday reality that belies the impression of stability, the illusion of separateness from the world. There's a breakdown of self as I and world as it, or self as subject and world as object, or self as knower and world as a thing that is there to be known. I think Wheeler had that part right. But I don't think, again, I don't think it means that there isn't an objective world. All of the structure that supports those distinctions disappears at the fundamental level and emerges only with decoherence. So I'm going to stop at the edge of the cliff here. It is the edge, I think, that quantum mechanics occupies. So you go one way and you end up in this sort of dizzying free fall of cubism. You go the other way and you end up on the solid ground of interpretations that try to erase superpositions and suppress interference. But I think the edge is both what separates and connects those two sides. So quick recap, one more sentence. The main point of all of this is interference arises naturally and inevitably for any system that's part of the domain it's representing. It becomes interesting in a connected domain where it's going to propagate along channels determined by the connections. Aspects of the world that are tied to our own actions can't be stabilized as objects of knowledge. In the classical setting, interference effects are channeled into the future. In a quantum setting, interference is in. I'm gonna stop my share.
Chris. Jenann, the dizzy free fall of cubism. With friends like you, who needs enemies? I'm glad I wore my green shirt today.
Is that it? No questions?
I mean, you know, I could play the objection game, but that's probably not so productive. Because, you know, I just discount ideas of compatibilism. I don't understand what choice means in a determined world. But that's a debate for us to have at the time. I thought the presentation, all the way until you get to the Everettian part, and I've told you this already, it was just beautiful and perfect. Nothing, you know, I couldn't improve it 1 ounce. So thank you.
Okay. I'd like to.
Sure, go ahead.
All right.
Can you introduce yourself first, please?
Yeah, I'm Spencer Rogers, and yeah, I want to say I thought the presentation was very beautiful and eloquent. I have this funny feeling every time I use a navigation app to try and find the fastest route from the freeway. my destination. And I think I've never heard this phenomenon of interference like explained so clearly. That was really nice. I do have a critical question though. So there's a slide you have of like results in quantum foundations, and you said something along the lines of, you know, that these results you know, say something about like the pre-existence of properties prior to us trying to observe them, or rather our inability to stabilize them. I don't know all these results all that well, but Bell's theorem, I believe, I believe denies specific types of theories about pre-existence of properties, like theories that involve locality. So I'm wondering if, you know, if we're willing to kind of stretch our minds and accept non-locality, how much of the rest of your presentation continues to apply?
It's a big question. So I had one slide where I bundled a lot of very different results under together, and I said that what these results show is that we can't hang on to the idea that the results of quantum measurements are there already or there anyway. I think Bell's experiment, Bell's theorem shows that we can't assume that the result on the other side of an entangled spin experiment was there already or there anyways, independently of the measurement we carry out over here. Non-locality is incorporated into the sorts of objective ontologies that I mentioned that are sort of realistic quantum ontology. So it's incorporated into the Everettian, it's incorporated into relational quantum mechanics. So I don't think it affects anything that I said. That said, you know, that one slide was, you know, bundled in a lot of careful analysis about what those individual results show and what are the different ways that one might take out of those results. So I said nothing helpful about to bundle it under that phrase that we can't assume results are there anyway, so they're already.